Let me continue prove Lax-Milgram theorem. Okay, so just to read Lax-Milgram theorem again. Suppose that we have by linear form A. Okay, but A is by linear form, and we have two conditions. One is A is continuous, and A is coercive. So coercive means AVV is greater than or equals to alpha times V norm squared. So here alpha is strictly positive, and the continuous means absolute value of AUV is less than or equals to m times norm of U times norm of V for every U and V are element in V. So then for every F is element in dual space, then there exists a unique solution U bar in V satisfying these equations. Okay, so here we are going to use ridge representation to prove this one. So let me start the proof. Okay, proof is the following. Proof. Okay, first of all, how do you approach this one? So for a fixed number, fixed element, for a fixed U is in V, then you can consider A, let's see, U is fixed, and then V varies, so this is the V to R. So you have any element, this one goes to AUV. So then this is linear operator, right? This is bounded linear. So this is a bounded linear. So that means U and this guy is element in V prime. Okay. So now you can apply ridge representation theorem by ridge representation theorem. There exists a unique element let's see, what do I say? UV element U. So what do I say? U VU AU. So then okay. So let's denote A of U. Okay, A of U. Element is in V such that AUV equals to inner product of A of U and then V. Okay, for every V is in V. So this is a ridge representation, and also the norm of, and also AU, the norm of this. So the norm of this one is the same as the norm of A of U. So this is V norm, this one is a V prime norm, operator norm, they are the same. Okay, so by the way, this one I'm going to change the notation here, not A of U. What do I say? I have a new A of U, so let's denote like this one. Okay, denote A of U. Okay, again this one also A of U. Okay, so I denote like this one. Then define, so then you can define the A operator from V to V. So you take any element here, the A of U equals to, you can, there exists a unique element, so A of U, I define like this one, okay? Then this is the linear, so you will, later on we're going to show this is the linear, and also then this is we are going to show this is linear. So for now we define this map, okay? And then we have another sense. So we have f is in V prime. So then by another Ridge representation theorem, by Ridge representation theorem, so here again there exists unique element G of F is in V such that so F of V equals to inner product Z of F and V for every V is in V, okay? So and then the norm of F V prime norm is the same as the norm of GF. So this is a Ridge representation theorem. Okay. So now what we want is this one. Okay. So the map is surjective. So now we want to show, first we claim that the map A is linear. We know this is a linear. We will show continuous, bounded linear, continuous, and then 1 to 1 and on 2. That's what we want to show. So first one, so A is linear. So A is linear. So why this is linear? So well, let's try to prove. A lambda 1 U1 plus lambda 2 U2. So let's complete this one. V. So by definition, this one, by Ridge percentage definition, A of lambda 1 U1, lambda 2 U2, and then V inner product, right? So this is linear. Oops, not this one, sorry. So that equals comma. Yeah, this is a bilinear form. So this, like this one. So now this is bilinear. A is bilinear, so this is lambda A U1 V plus lambda 2 A U2 V. So this is by definition. And then again, this one is this is again A U1 V plus lambda 2 A U2 by definition V, okay? So finally, you can bring, this is another inner product property. So this one is lambda 1 A U1 plus lambda 2 A U2. So we have this one for every, so this is true for every V is in V, okay? So that implies, and this one equals to that. For every V is true, so what we have, so A lambda 1 U1 plus lambda 2 U2 equals to lambda 1 A U1 and plus lambda 2 A U2. Okay, so this is a linear. And then second, and linear and continuous. Okay, at the same time. So let's prove at the same time. And you compute A of U norm squared equals to, by definition, AU inner product with A of U, and this is not by definition A of U, AU. Okay, yeah, this is true. But this guy is less than or equals to absolute value of U and AU. Yeah, this is true. And this one is less than M, norm of U, norm of A of U. Okay. So if A of U is non-zero, then you divide by A of U. So A of U norm is less than M U norm. Okay. And what if A of U equals 0? So A of U norm equals 0, then this is always true. You know, this is always 0. It's always true. M times U norm, right? No matter what right hand side is, this is always true. This is always true. Always true. If the norm of AU equals 0. So therefore, what we have, A of U norm equals less than M times U norm. So that, which implies A is continuous. Okay. So bounded means linear map is bounded is the same as continuous. Okay. Linear operator. So we proved the map is linear and bounded. And then next we want to show A is 1 to 1 has closed range. So second part we want to prove A is 1 to 1 and has closed range. So that's what we want to prove. So that means we want to show the kernel of A equals 0. Range of A is closed. So it equals range of A. So that's what we want to prove. Okay, so first one. Well, so we by definition alpha times norm of U squared, and second, this is by second condition. So this one is A U U. So here, because A is coercive, so coercive we use coercivity over here. And then by definition, this one is A of U inner product with U. Okay, so this one is less than A inner product AU U. Okay, that is the same as less than or equals to A of U and then U norm. Okay. So this one implies if U is non-zero, U is not 0, then alpha times U norm is less than norm of A of U. So that we conclude here. So this implies, so what? So what? This implies that if A of U norm equals to 0, then U norm has to be 0. Okay, U norm has to be 0. So that implies U equals 0, right? If U is non-zero, then we have this inequality. the u equals 0. So from here we have contradiction, right? So if u equals non-zero, then au 0, u is 0 is non-zero. So from this inequality, so we are done. So this implies so if we want, if you have a little bit confused, then you remove this part, remove part. So if a equals 0, a equals 0 over here. So we leave here. So we don't need to divide by something. So then from here, alpha times norm of u squared is less than 0. That implies alpha is strictly positive, so u norm has to be 0. That implies u equals 0. Okay? So that means kernel A equals 0. Only 0. So if kernel, yeah, okay, that implies A is injective, 1-to-1. And then second part, let's try prove the range is closed. So range of A equals to range of A. So, well, this is always true. This one is always true. We don't need to prove. This part we don't have to prove. Always true. So we need to show that RA closure is a subspace of range of A. Okay, so let's try to prove this one. So let's take one element y is in range of A closure, and by definition, then there exists yn and sequence A sequence in range of A such that yn converges to y. Okay, as n goes to infinity. So now since yn is in range of A, so there exists some element un is in V such that A un equals to yn, because this is in the range. So by the way, yn converging to y, the convergent sequence, y is Cauchy sequence, right? So from here, yn is Cauchy. Any convergent sequence is Cauchy sequence. So we have a Cauchy. So here, what we want to prove un is Cauchy. So now you compute uk minus ul. What is this one? ul. So norm of this one, what is this one? So this one alpha times this one squared. This is again you use the computation, you follow this one, you replace u by ul, k minus ul, you have this one, right? So we use this one over here. The same here. Okay, over here you apply that, you have less than or equals to norm of A uk minus ul and norm of uk minus ul, norm like this one. Okay. So, and then this is the same as A uk minus A ul and uk minus ul. And this one is y k minus yl norm UK minus UL norm. So now if norm of UK minus UL is non-zero, then which means UK and UL are different, then what I have, UK minus UL norm, you divide both sides by this number, this one, then you have 1 over alpha UK YK minus YL. So I have here, if UK equals UL, then they're the same, we don't worry about. So this implies that, so this here, we know that this YL is Cauchy sequence, so this is Cauchy sequence. So this implies that since this YK is Cauchy sequence, so we end up with the KL is also Cauchy sequence, Cauchy in V, okay? And V is a Hilbert space, so since V is Hilbert, complete Hilbert space, so UK converges to some number, so UK converges to U in V as K goes to infinity. So then what? Ym equals to A um, that is UK converges to U, so AU, because A is continuous. So we know A is continuous, so we end up with this one. So, but what is Y? So originally, Y is converged to Y, right? So since Ym converged to Y as M goes to infinity, so we have this one and this one should be the same. So AU equals to Y. So that implies Y is in range of A, okay? So what we have, we start with the element, we choose Y is in range of A closure, we end up with Y is belongs to range of A. So therefore range of A closure equals to range of A, okay? Yeah, this is second one. And then number 3, we are going to prove A is surjective. So now I'm going to prove A is surjective. So let's just see how we prove this one. So surjective means range of A equals whole space V, okay? For now, so let's try to prove this one. We know range of A is closed subspace of V, the closed subspace. And then you can decompose. Then V can be decomposed with the range of A, orthogonal, they're orthogonal each other. I can write that in that way, okay? So if RA is different from V, then there exists the element in the range A orthogonal. Okay, this is a non-zero element. They are not the same, then we have non-zero. If they are the same, not the same, then we have non-zero element. Okay, so then we compute A of z. So A of z is in range of A. Okay, range of A. And so we have AZ. Z has to be 0. But this one, by definition, A, Z, Z, right? By definition, this A, Z, Z. And then by coercivity, this one is greater than alpha times G norm squared. Okay. So here, that's why we need the coercivity. So here we use coercivity. Okay, here we use A is coercive. Coercive. So we use this one. So that implies the alpha times, also alpha is positive. So this one norm is less than 0. So that implies Z norm has to be 0. So we have Z has to be 0. So but this is a contradiction, right? Z is non-zero, but we have 0 here. This is contradiction. So this is a contradiction. So therefore, this contradiction. So we have, hence, so we have a range of A is a whole space V. Okay. So A is 1-to-1 onto. Okay. So the map A is a 1-to-1 onto. So therefore A is V to V is 1-to-1 onto. Okay. So from here what we have. So in the beginning, you remember for every A in A V prime. Remember this one. Remember for every V prime, there exists the unique Z of F is in V such that F of V equals to Z F V. So for every V is in V, right? This is rigid representation. At the beginning we have this one. So we have this statement. Then by definition, so the map A is 1-to-1. So you have, whenever you have ZF, then you have a unique element corresponding to V, right? So there exists a unique element. U bar is in V such that A U bar equals to ZF. Okay. Yeah. So we have this one, and also what we have. We also know that U bar squared alpha is always less than norm of A U bar, and then U norm, U bar norm, and this guy is norm of ZF, okay, and then U bar norm. And then what this one is, ZF norm is the norm of F norm. So this one is norm of F norm, V prime norm, and the U norm, U bar norm. So I have here. Okay. So again, if U bar is non-zero, then again u bar norm is less than or equals to 1 over alpha f v prime norm. And if u bar equals 0, then this is always true. Because whatever right hand side is, this is always true. Okay, this is always true. Okay, so this from this statement we conclude that so u bar norm is always less than 1 over alpha norm of f v prime norm. Okay, so we have this one, and then from this statement also we have a u bar v. What is it? By definition, this one is inner product a u bar v. Okay, this one z f v. This one f of v. So for every v is in v. Okay. So finally, we rewrite this one. We end up with getting the so this implies u bar is in v is the unique solution of a u v equals to f v for every v is in v. Okay, this unique solution of this equation. Okay. Again, u bar is norm is less than 1 over alpha f v prime. So finally, we proved unique solution existence, unique solution of these equations. Okay, so today I just give you the Lax-Milgram Theorem, which is one of application of ridge representation theorem. Then from Lax-Milgram Theorem, we can prove existence of many partial differential equations or variational form of differential equations. Okay, so I'm going to stop here. We will see next time.